Okay, let's go through and really talk about why resistors and capacitors add the way they do in series and in parallel. Again, there was another video on resistor fundamentals and capacitor fundamentals that I just kind of gave you the ideas, but I want to talk about why that's true. Okay. And really, you know, current and charge are going to be very similar in terms of reasons, and then voltage in parallel and series is very important. So let's take a battery and let's look at two resistors. And again, this is a series. We'll call this one R1 and this one R2, and this is a certain voltage. Okay, so what do we know is true? Well, we understand that if we go around a circuit and we do the loop rule, okay, so this is the loop rule. If you haven't heard of this yet, eventually this will be Kirchhoff's law that says that the sum of all the voltages around a loop have to equal 0. And all that's saying is that the gain of the battery, the voltage gain of the battery, has to equal all the losses here. And so, well, how's this loss? Well, remember, Ohm's law says that V equals IR. So if you want to know the voltage drop over a battery, just tell me the current in the battery, the current in the resistor, and the resistance, and then I will tell you that. So what we can say, let's do this loop rule. The loop rule says that I'm going to gain some, right, the voltage, but the total voltage of the battery, the gain of the battery, has to equal then the losses over the resistors. And again, I can do this minus this equals 0, or I could just set the gains equal to the losses. Hopefully you're okay that those two are saying the same thing. The gain of the battery equals the two losses. Well, what is that? Well, V equals I1 R1 plus I2 R2 based on Ohm's law. However, what's our knowledge of current, right? The battery causes the flow of current this way, this way, this way, right? Down through this, and then across, and then you're back. That's the flow of the current. So how does I1 compare to I2? Well, current is the flow of charge. Charge goes through this at a certain rate, and charge goes through that. The current through R1 and R2 is the same. It has to be. Where would the charge go? It's not like a certain amount of charge can flow through this guy and then not flow through this guy. And so I1 equals I2. Okay? Again, I1 equals I2, so we can get rid of that. And what we can say then is that the total voltage is what? Well, the total voltage is just the total current times the total resistance. I1 and I2 is the same thing as the total, because the total current does flow through that. Again, this is finding the total resistance. The total voltage is the total resistance, the effective resistance of the system times the total current. But I1, I2, and the total current are all the same thing. Those all cancel, and what you're left with is that the total effective resistance is in fact R1 plus R2. And so we've derived the fact that if you have two resistors in series, the total their total resistance is just the sum of those things. Okay, and there's no way around it. And again, the fact that we know that the loop rule has to be true, the gains have to equal the losses, and we also know that the total current in a series case does equal the current through the first one and the current through the second one, which allowed me to replace those by I, and then I could cancel an I from every term. Okay, now let's do it in parallel, and I can show you why they add that way if they're in parallel with each other. Okay, so this is R1 and this is R2, and here we could use the loop rule again to show that that gain, this voltage gain, and if I do this loop, has to equal that loss. But then that gain has to equal that loss. So what does it say about two things in parallel? And this is not unique to resistors. Anything in parallel has to have what? parallel things have the same voltage, have to, based on this loop rule. And again, you can think about how if I go this way or I go this way, I have to get a gain and a loss, a gain and a loss. So these two losses have to be the same. And that's true whether they're both resistors. They could be a resistor and a capacitor, or a resistor and an inductor, or whatever else you want to put. Two things in parallel have to have the same voltage drop. Again, it's the same voltage here and the same voltage here. This is at a voltage of V, this is at a voltage of 0. Both of them have to drop a certain voltage. And so what we can say is that the total voltage does in fact equal the voltage drop over 1 and the voltage drop over 2. Okay? So that this is something we need to know, and again, that's true for all parallel things. Okay, now let's look at the current. So the current, the total current goes this way. But what does it do? Well, some of the current goes that way, and some of the current goes that way. You literally can think of current as the flow of electrons, right, per second, coulombs per second, and it gets to this junction point, and some of the charges are going to go this direction, and some of the charges are going to go this direction. But the total current, I, has to equal I1 plus I2. It has to. There's no way around it, right? You think of if this is water flowing or this is people walking, whatever you want to make this flow at this junction, so many people per second are coming in. Some people walk this way and some people walk this way. Okay, so this has to be a true statement. But then what are these? What are these? Well, the total current, going back to Ohm's law, can be written as the total voltage divided by the total resistance. If we looked at the current through R1, well, that's just the voltage of 1 over the resistance of 1 plus the current through 2 is its voltage divided by its particular resistance, right? I'm not claiming that these two currents are the same. I'm just saying that they equally come from the total current. And then look at this. But if V equals V1 and equals V2, then all of these are the same. And now I'm done. I've just shown that 1 over the total resistance is equal to 1 over R1 plus 1 over R2. And now I've shown you why, again, the reason behind why in series resistors add and in parallel their inverses add. And again, it kind of just goes back to how things work. In series, these two things have the same current, which allowed me to get rid of the current. And again, I'm really just doing Ohm's law. And then in parallel, I know these things have the same voltage. Voltage here, voltage here, voltage here are the same, which allows me to cancel these voltages. And I'm left with doing Ohm's law, and I'm getting the effective resistance. Again, hopefully this is enough proof for resistors. Now we're going to do the same thing for capacitors. We'll just use Q equals CV instead of V equals IR. Again, this is the reason as why. So let's go to capacitors. So capacitors, the fundamental principle here is Q equals CV. Okay, so let's look at capacitors in parallel. So this is a parallel capacitors. Okay, so this is capacitor 1 and it's capacitor 2. They have capacitance C1 and C2, and this is a battery with voltage V. So what do we know is true? Well, they're in parallel. So we know then that V equals V1, which also then equals V2. Okay, they have to have the same voltage because they're in parallel, right? Same voltage in parallel. Doesn't even matter if they're both capacitors. One could be a capacitor and one could be a resistor. They still have to have the same voltage. Again, that's really kind of the loop rule. But we also know what happens to this charge. Well, the battery is going to supply this total charge. So this total charge is coming this way, the total charge, and some of the charge goes here, and then some of the charge goes over here. Oh my goodness. Don't make those positives. Those are negatives. And then some of the charge goes over here. Okay, so let's say there's more charge on C2 than on C1. It'll end up just being that C2 is just different than C1. Okay, so let's say there's more charge on this guy. But what happens? Well, think about it. The total charge has to be Q1 plus Q2. Right? The total charge that the battery supplies and separates is the combination of some of the charge goes here and some of the charge goes here. So this has to be a true statement. But what can I do? Well, I can take the Q total and I can use this law that Q equals CV and say that the total charge comes from the total capacitance times the total voltage. Q1 is just C1 times V1. Q2 is just C2 times V2. But what do we know about all the voltages? They're the same. And so then the total capacitance, right, the total ability for this system to store charge, is just C1 plus C2. And again, if you think about the charge here, which one of these can store more charge? Well, they get the same voltage. So if they get the same voltage, if voltage goes up, if the capacitance goes up and the voltage stays the same, then the one that has the bigger capacitance will store more coulombs based on the fact that they're getting the same volt. So this would indicate if this stores more charge, that C2 in this case is bigger than C1. If they're the same, then they're going to store the same amount of charge. If C1 was bigger, then it would get more charge again, because they have the same voltage. And if they have the same voltage, the bigger capacitor will end up storing more of the charge. And it's actually proportional, right? If this is double and this is, then it will store double. Okay, so it would get like 2/3 of the total charge, and this would get 1/3 of the total charge, because we know the total charge has to add. All right, this is in parallel. So in parallel, capacitors add, just like resistors added in series. And then if we put capacitors in series with each other, okay, so now I get C1, C2, and a certain voltage. Okay, what's true here? Well, now we have to do the loop rule, right? This and this and this. So V has to equal V1 plus V2. There's a certain voltage drop here, and there's another voltage drop there. Again, loop rule here, that loop and that loop. So these two losses have to be the same. Here, these two losses together have to equal the gain of the battery. And think about how this works. What's V of the battery? The V of the battery is the charge the battery is supplying over that capacitance of that system, right? These are like Q total over C total. V1 is this voltage drop. Well, that's just Q1 over C1 plus Q2 over C2. And now we have to think about it. Okay, how are these charges related? Well, this one's the hardest one. This is the one people screw up. And I'll just remind you that it's very, very, very similar to what we said about two resistors in series. Okay? What did we say about the current that flows here? We said that I1, that I equals I1, which also equals I2. So current is flowing this way, and it goes through here, and it goes through here, and so the same current that goes through R1 equals R2, which is the current that's produced by the battery. Again, in series, they get the same current. Well, here, we're not talking about the flow of current. Now, when you're charging this thing, I understand that current is flowing, but current doesn't flow over this capacitor. What you're doing is that you're taking negative charges from here, and the battery does work on those positive charges and slaps them up here. The battery can't do anything to this plate and this plate, but it takes positives from down here, does work on them, and it puts them on that upper plate. But whatever charge it takes from here, it puts here. So if it puts 4 up here, it's got to leave 4 negative down here. Now inside here, that just polarizes all on its own. Polarizes all on its own, because these positives are going to attract 4 negatives from this bottom plate, or the top plate of the bottom capacitor, and then that would leave that one a net positive. And hopefully you can see that whatever I put here comes from here. Those two plates will then polarize these interior plates, and that you'll see that the charge here equals Q1 and equals Q2. And it's just like this situation where two resistors are in series and they have the same current flowing through them. Here, two capacitors in series have the same charge on them. Q equals Q1, which equals Q2. And so then you can come here and say those things are all equal, and then they cancel, and then you're left with the expected result that the total capacitance is indeed 1 over C1 plus 1 over C2, and now I've derived exactly that. In series, the inverses of those capacitance add to find the total capacitance. In parallel, capacitors just add. Resistors are the opposite. Resistors in series add, and resistors in parallel add inverses, and it's just because how the relationship between I and Q are kind of opposite of each other, right? Again, these have the same current, these have the same voltage. That kind of difference leads to this different addition. Again, we need to find the effective resistance of some system, just like we need to have the effective capacitance of some system. It's going to be really important. And again, I've derived both of these things. You can kind of think through, but certainly same voltage for capacitors in parallel, same voltage for resistors in parallel. That's just true because they're in parallel. Same current in series, same charge in series. We're not really looking at the flow of current in this, even though we are charging this. And at the very beginning, current does have to flow to kind of rearrange these charges. But once they're there, these charges get accumulated, and they come from the fact that we have to leave this then negative, and then these inner plates polarize. Again, capacitors in series have the same charge, just like resistors in series have the same current. Capacitors in parallel have the same voltage, just like resistors in parallel have the same voltage. So they're very similar, and they lead to slightly different results just based on the relationship between Q and I. Okay, hopefully this helps kind of understand why those formulas are what they are.